Good morning, good morning, everyone. I hope all of you are doing fine. And today we are also going to look at one of the topic, which is what is 3D or what is turning 3D in our hardware systems, right? Because we are going to talk all the way to the hardware systems. What is hardware systems? So when I say hardware systems, means you know we are talking about processors and beyond, right? So a very good example of a hardware system is um, is the AI hardware which NVIDIA shows, right? Where you see a H100 system. It's a system. So that is what we are going to explore. That what is basically turning and why there is a need for 3D at different abstraction levels. One would see inside a chip, processor, and a system, right? So we know that the system may look like something which has multiple chips, multiple memories, right? So these are maybe your GPUs or CPUs, what you have, right? And then you have your memories, right? Which could be there. So this is your mem. So that is, and then there are buses which are connecting these, right? So which is connecting from GPU to GPU, then there is a memory to this. So this is kind of how we draw the architecture of a system, that how the computing systems are built, right? And a very small subset of this is a processor also, which we build multi-core. But this is so then there is a boundary is something which we can define with when they are made on different chips, right? So let's say which we are going to also see when we, how do we say that this is the processor or this is what is a computing unit, right? One unit computing unit. So the question we are asking is, in this system, what is the need for putting 3D? So obviously, you know that all of this demand, when we are connecting all of these things together, one of the thing, and these are constant across different levels, which you will see that you would want your speed to be higher, your energy to be lower, right? Or energy efficiency to be better for these systems, so that how much you are spending, and the area also should be lower. And there's this relates to the cost, but it also relates to sometimes the speed, because we see that if the GPUs are far apart, then the way or the line which is connecting them would also have a lower throughput, right? So the speed at which you can send data would be also limited. While they are closer, then your delays in the uh, giving the data would be lesser, right? So that is what simply would mean that how the you want to make the area better. So now this is the same way we go. Now we zoom in into a processor, which is what we have been talking about, and we see that okay, there is a silicon. So then when we say there is a silicon, and this silicon we have talked about is let's say a piece of silicon, basically, though it is a wafer. So this is your piece of silicon, right? And in this silicon, the typical diameter in the industry we use is 12 inch, which is 300 millimeter, right? So that is the wafer diameter. So now you see that what happens as a result of this is that this wafer, when we are fabricating, obviously we understand that we could put the whole system into the wafer also. There's a possibility that we would like to put this into one wafer. The thing is, there are multiple challenges when we do that, but that is, there is a possibility of doing this. And that if you are interested, you can check out something called wafer scale AI systems, right? In Cerebrus, and there are companies who are looking at this wafer scale AI systems. So that means putting everything, all what we were talking about, memory, GPU, everything on wafer, right? On the silicon wafer. So that means, why do one want to do that? Because we know that when we are integrating them together, that is the whole idea of why. So let me just walk you through that the thought process, what is happening. So you see that you have used a breadboard. I hope that you have used a breadboard or not. You have seen some circuits where there are these holes and these discrete elements like resistors, then capacitor, they are connected, right, together on a breadboard. So these are we know as the discrete components, right, which you are connecting. And a transistor, let's say. So these are all connected on a board which are discrete components. So you have seen the pain of making that circuit work robustly on a breadboard just from the robustness point of view itself. Then obviously when you are having them apart, because you can only put in discrete into whatever holes or whatever system you have made, you see that the connections could be also one of the very big problem to do this reliable way and in very optimized way. And that is where the idea of the IC came from. That IC means that everything what I need, can I put it on a silicon wafer? So if I need a MOSFET, I put a MOSFET here. If I need a resistor, I put a resistor here. If I need a capacitor, I put a capacitor here, right? So all of that can be put on silicon, and then I would use the metal layers. So there are multiple metal layers in the back end of line, which is, so this is what where these components are fabricated, is what we know as the front end of line. Where these connections are made is what we call as the back end of line. That is the traditional definition of this, right? So what happens is, then you want to connect, you go from wherever the space is available. It's basically connecting two cities or two houses, or so basically you are trying to find the road which is the most optimum road to reach from there to there, right? So you may find, okay, this is the road which is an optimum road, but to connect to capacitor, maybe connecting this on this is not a good idea. Let's go to the highway then, and then from this highway then we connect back to this, right? And that is where obviously this is not done by a person anymore, right? These connections and everything, and there are tools in the industry which we know as the EDA tools, right? And typically some of the physical design tools which do this kind of thing. That, and this is what we know as the routing, right? Routing means that connecting these different things and making sure that you meet the timings and everything which you want to meet, right? So all of that then that means that clearly you see the advantage of putting everything together, and this is what we know as the monolithic system, right? So if you hear this word monolithic, it is basically this, right? This is what we are talking about. So monolithic system. So monolithic means on the same stone, or the lithic means it comes from Greek word, but on the same stone you are litho. Litho basically came from that you are doing the printing on the same stone. So on the same stone you are putting these elements and connecting these elements, right? Mono means single. So now that is what we plan to do, right? And we want to do, industry wants to do, integrate everything on the same, so that because we have the technologies to do that, right? Now the question is that component which we want to do, can it be integrated on silicon, is a big question, right? And that is where you see that in RF front end, even in your transceivers what you have in mobile, not all the systems are on chip, right? So that is what the typically the definition people ask is on chip or off chip, right? That is what they discuss this. So one of the very classical example is the inductor, which you don't see in FEOL, right? Though there is a way that we can put some on chip inductor, but they have their own problems of the losses and everything. So that is the reason why people try to put them off chip. So that means there is chip which you have, right, which you have fabricated from silicon, right? This is made of silicon, and then you put a inductor here, right, separately, and then you will connect, let's say, whatever your ports were, and then you will connect. So this is an off chip inductor then, right? This is one of the example why you see that when you are integrating these elements or these chips, and very good example of that is in a microcontroller Arduino kind of a system, which you would have all, if you've seen in the Arduino, you see that there is a plastic board, right? This is the board, and on this board you see there is a some processor, some ICs are connected like this, right? And then there are some traces which are connecting. Traces means is a copper traces which are connecting these lines on the board, right? So this is what is also known as the board assembly, right? That means we are assembling different chips. So let's say this is chip 1, chip 2, chip 3 on the board, right? And why we could not, we have to do it separately, because in an integrable system we could not have done it. Or when somebody is fabricating chip 1, he does not know what the chip 2 would be. I mean, if he knew, because the person who's integrating the system is making this in this way, so that is his design, that how chip 1 and chip 2 are talking, right? If one industry tries to, and this is something they can integrate, they will integrate and put it together for offering that, okay, you can use the whole thing together. And which we know is typically, if the multiple chips are coming together and put is something in a microcontroller, right? Which you would have heard, the microcontroller like ESP32, this, that microcontroller, that micro, because there are multiple chips which are put or integrated in a fashion that they are closer to each other, right? uh, so that is the basic idea why you want to put everything or integrate everything. That is the central idea of doing this. Now let's go back to our silicon. So silicon, we already talked about that this was about 775 micron, right, for the two, and this is one part of the die. So this small square is what you see, that when you are dividing this wafer into, right, multiple dies. So this is just one piece of that, right, which is what we are drawing here. So now you see that in this, this is what we know as the die, right, or the chip is when it is processed. So with the die which is not processed is just silicon, right? There is nothing. But chip is what is the processed die, right? Processed die means that when you have put in the elements or the components which you want to put on silicon, right? So that would we mean. Now there we saw already one of the very classic example is the MOSFET. We saw, okay, you can put in a MOSFET, let's say, like put a metal, let's say oxide, right? And then you can put in your contacts there, whatever you want to put, right? Though I'm drawing very big compared to the die. So typical die size, let me give you some size. So typical die size could be, let's say, 10 mm by 10 mm, right? This is the size of the die, right? This is the size of, let's say, bare die. This can change based on the requirement. Let's say Apple, typically in Apple processor, you see some dies can go to 20 by 20 also, right? But typically that is the size, and can come. So this may not be always square also. Square also, it can be rectangular, right? Depending how your processing or how your system design is basically. And here we see that if we are talking about just the footprint of this transistor, right, this MOSFET, this we are talking in, let's say, in the current technologies, we are talking somewhere around 50 to 50 nanometer, right? So 50 nanometer by 50 nanometer. That is, you can calculate if you were to divide 10 by by 10 right, by 50 nanometer, right? So each is 10 power minus 3, 10 power 6, so 10 power 6 into 10 power 12, right? So you can calculate that how many transistors. So you already see that you are somewhere in the billions, right? Billions of transistor on the chip. So that's what you hear in the current technology, that there are billions of transistor on the chip, is because of this, because your die area is very large. And this, now to connect them again, you need these metal layers which we talked about at the back end of line, right? But what is turning 3D? So because you see that the die area is very precious to you, right? You don't want to increase die area, but you want to pack more and more transistor on top of that, right? That is the key thing which we want to do. So one approach would be, obviously you can say, is that you want to reduce, or you would reduce the footprint of your transistor, right? Of, so how to increase number of transistors on a given dry area? First is obviously reduce the footprint of the transistor. It's basically like Mumbai. In Mumbai, if you have less place, right, more people to live, obviously you reduce the sizes of the houses, right? That's why you see it's very efficient in a way that it's like a single BHK. A lot of people are living in that kind of thing, because you have reduced this. You can reduce it, which is what we know as the Moore's law. Right? That's what the Moore's law was, or the observation was, governs. that you reduce the footprint of the transistor, and that's what industry works on, that how can we do this and all of that, right? That is what one. uh, so now to do that, how would you reduce the footprint of the transistor, right? That is the question you would ask. So one would be, if you see the transistor, let's just draw the transistor again. So this was a transistor where there's a silicon, there's a metal oxide, right? And you see this was this and this, right? This is our planar old transistor, which we have seen. We have been seeing for the operation mostly. Um, Now you want to reduce, you to see this is one dimension and another is that dimension, right? Because thickness is not important, right? This is anyway decided by the wafer thickness, but this is your width and this is the L. But this L is the total transistor, right? Channel length is separate, which is what we know as the channel length or the gate length. But this is the total L of the footprint of the transistor, L foot, let's say, right? This is W of the transistor. So now how can we reduce? Obviously, you see clearly LCH as one indicator that you can reduce LCH, and that's what we were talking about. When you try to make this LCH lower, you see that in this configuration, you are not able to get this much gate control. And that is where we talked about in one of the video, if you see, um, that what could be inside your or what is already inside in your processor, or what could replace, what material can replace. So this is in one of the video. You can see that the we talked about that this transistor now is turning like this, that the silicon is this much thin, and then you put oxide on top of each other, sorry, across around the silicon, and then you put metal around this, right? So that is how typical transistor, which we know as the gate all around transistors, right? They are turning, and this transistor is already kind of 3D, right? Because you have moved away from 2D and you're putting this on a substrate, some substrate, right? Like silicon, obviously, and so that means we silicon and silicon dioxide, right? And then we put this on the substrate, and then you're making these devices. So now the question which comes is that um, L foot is something, okay, I'm trying to minimize, and that is what I'm doing. That by reducing the LCH, I can reduce the, and for doing that, I need to go for already some transistors. Now, does it solve the problem to just make the transistor wrapped around? Can it give me can I increase the number of transistor in the given footprint? I can to certain extent, but what would be nice is, you see that now, because you have put the transistor like that, you have opened up a space for you in the vertical direction, right? Where you can stack these transistors. So let's think of this. This is one transistor, let's say, right, which has obviously this oxide layer and metal layer around it, right? Then there's another transistor where there is another layer around it, right? Like that, I could put in the vertical direction all this. So you see that you are already now going towards 3D, right? So transistor itself becomes 3D, because now this whole thing is what I call one transistor, which has turned 3D. The reason is because I'm trying to get the transistor performance increased within that area, right? Because the footprint has not changed. This is the L foot, let's say, right, or W foot, and the other direction. Yeah. So this is in this way. This would be L foot. Let's get W and L. That does not means basically it's the footprint of the transistor, right? So because transistor would look like this. So this is the footprint of the transistor. Because you have now utilized the third dimension, you could put this transistor. So this is your transistor one, right? Two, three. You are putting on top of each other. So you have already turned the transistor itself 3D in this particular idea. Because how did you do that? Because you wanted to pack more and more transistor in the given footprint, right? That is the main goal there was. So that is the one thing you would see, things turning 3D, or they are already turning 3D in the transistor level. And now people are even talking about where you have, as of now, let's say this is still NFET, right? So as of now, the idea is that this is NFET and the PFET, they are different, right? So this is, let's say, one FET, either NFET or PFET. So now in future, people are thinking, why to make this like this? Can't you make on top of this, right? So that means you are again saving much more area because you have moved your NFET on top of PFET, right? So that is what would mean ultimate scaling in the terms of area, at least from the CMOS technology point of view, which you can see that your PFET is on or NFET is on top of PFET, right? So that is what they know as the CFET, complementary FET. Okay, so this is, and then the way which in the video of what material can replace, we have already talked about what, like how the promise of the 2D material for channel is there. So that has been talked about in that material perspective. Now we are talking about from the dimension perspective, what drives this 3D. So is this the only 3D you are going to see, that the transistor becomes 3D? No, everything becomes 3D at different levels. So what is this transistor doing? So these transistor, as we said, this is a white silicon die. On the die, these are going to connect to each other, right? These transistors, they are through the metal layers. So these are your back end of line, right? So through back end of line, then you will connect these things, right? So then question is, again, we want to pack much more transistor, right? That is the main thing. So you said, okay, you made this block of thing where there are multiple transistors which you are making, right? But this block is also now going to be connected through metal layers, right? So these are the metal layers which are going to come, all right? So which is your back end of line on top of that. So the question is, okay, you are doing, still you are processing all of this in the front end of line. Front end of line means just on the silicon wafer, wherever the wafer was, right? But suppose if I were to fabricate transistors there, right, some transistors here also, would I not increase the number of transistors in a given footprint? Yes, I would. And that is what of the direction you see again, which is the area of the BEOL transistors, right? Back end of line transistors. Can I fabricate there and get some added benefits from that? And there are many technologies people are evaluating, like if you heard some oxides, basically like IXO and so, which comes from the display technology. So those things are being evaluated, the amorphous oxide AMOs, for this kind of application, right? So that opens up that space of the back end of line. Okay, so that see, the greed is driving that, right? The greed of putting multiple transistors in the given footprint. That is the main point there, right? Now, what else is it? Is it only the transistor which we worry about? No, we worry about the whole system, right? So you have made this chip. You have made this chip. Let's say whatever that chip is, and you have put in all this nicely 3D and everything. Now you know that you are going to put this on the same chip. You are going to also put SRAM, right? Or the cache, which we know as, right? Right. So this is the cache which you are going to put. So the SRAM cell also, let's say this is the SRAM array. Now the question is, when we put, so for example, one way again would be that you put your processing here, right? This is your processing or computing elements. And the another is you put your memory or cache here, right? And you say, why, if you can just put that on top, if there's a possibility, why not put them like this, that the chip or the processing is here and memory is here, and then the even the interconnects which go from this to this, you have reduced once you put on top of each other. And that is what people are also exploring, which is the 3D integration, right? uh, because now you are integrating the different chips, right? You are integrating, let's say, processing chip and memory chip on top of each other, and this is the cache. And the technology or the interconnections which you can use, there are multiple ways to do that and enable that. But that is the basic idea, and ARM has already demonstrated that in one of the processor, the 7 nanometer processor. So you can check this, the 3D integrated cache or SRAM on top of a processor, right? On top of it. So this has been shown. Wow. So that means you are able to put now chip on or a memory chip on top of it. But does it stop there? Because system is very big. You told me there are many memories, there are many computing. Yes, in the future you may see that you would need another substrate, right? So in one substrate now, as of now, if I were to put two CPUs, one approach was like this, that I put this is CPU 1, this is CPU 2, they are put in together and then they are talking to each other, whatever wires they have, right? But now in future, why can't I put them together? So everything you are thinking of stacking, right? This is your CPU 2, this is your CPU 1. So this again 3D, right? Because you put in on top of each other and on whatever substrate you are putting, there's many different, whenever you see this kind of folding happening, you always see that the 3D is going to give you an advantage, and this is driven by reducing the footprint of that thing and making the connection and the more shorter when you are connecting this through like this, right? So that is the idea with when you see of which we know as the 3D integration. And in future you may see many technologies put in together like this, which is where you say heterogeneous 3D integration is the word. Heterogeneous means multiple technologies or many different technologies. For example, we may see, let's say, for example, I can give you one example where you have, for example, you are making a camera, right? So you have a substrate, let's say silicon substrate you start with. There is a processing layer which you have on the bottom. On top of that, let's say you put a memory, right, layer. On on top of that, let's say for example, you put a camera layer or the image sensors, right? So now how this is going to work is, you see your image sensor is going to talk to memory. So whenever you take an image or pixels are saved here, they are processed in that, and then you see that it is saved into one of the intelligence. Or if you even have a camera which has the AI intelligence, let's say if you say I am designing a camera with AI intelligence, where is the intelligence? Camera does not have an intelligence, right? Intelligence comes from these processing units, right? Memory and the processing. And that if it is integrated on the same system, you see that how beautiful that would be, because then you would get everything very energy efficient and so, right? Because the sensors are very nicely integrated with this. And that is what the true potential of 3D integration would be. And I think it's a very exciting field as of now, which we are entering into, where a lot of things are being looked at again, that can I integrate it better, right? So it's a whole game of integration, right, at that level, if you see. So that's why if you are, even if you study devices, do not limit yourself to just study the physics. Think of the bigger picture also. Where is this device going to be, right? Which architecture which it can go into, or how it would go into the physically on the layout of the IC. So that is what you also imagine, right? So don't just build the house, also think where this house is going to sit, what would be my nearby environment, what would it needs to talk to, right? So that gives you a more holistic picture of how the industry and everything is going to evolve, and how that thing is going to affect whatever you are doing on a daily basis, the transistor design or a material design, or whatever you invest your time into doing in semiconductor, you would be able to have a better sense of doing that, right? So that is what my takeaway from this would be. So I hope all of you keep learning about 3D and the field we are entering, where we are integrating things either at the system level. So this thing which we talked about is obviously system integration. This we were talking about for the devices is a device integration or 3D device, right? Where you are integrating at the device level. And we saw the chip integration also, which was this chip integration, right? And one of the very nice example of chip integration is what we also talked about in HBM in an AI system. So as of now, if you see NVIDIA system, these things which I drew in NVIDIA system memory, it's called HBM cubes, right? So high bandwidth memory, which high bandwidth memory, how it looks like, it's just a series of DRAM dies which are integrated on top of each other, right? So this is another example of 3D which you see in HBM die. They are all integrated on top of each other, and then connected through something called through silicon vias, right? So which are going across the dies, and then you connect these dies also through connections like copper interconnect and so there are multiple ways that you can see this 3D is being used in the industry, and this is again at the chip to chip level, right? So this chip to chip level, I would say, but it's not inside the chip, but yeah, it's a, or we say that this is the chip to chip, but the whole system also, one would think in the future that how we can integrate them together, right? So that becomes a very important enabler, or different kind of systems or different kind of products one can see also in the market. So if you are someone who is very passionate about this thing of building different products with these technologies, so I think this is one of the playground which you can think of what each technology offers, and how does one integrate them, right? What technology which is already present which one can use, which let's say Nvidia is using very specifically with the TSMC, like CoWoS, CoPoS, so Info. So there are multiple technologies for this 3D integration which TSMC has, and Nvidia is one of the biggest customer or client for using these technologies. So that is how you can also think that in future, if you get access to these technologies, or what can be done in that space, that one can plan or design these systems better than other, right, for their applications or whatever they are thinking, such as that's a camera with AI intelligence. Okay, with that, I would end here for today, and thank you for listening. And hopefully, you all keep learning and keep growing every day. That is what the idea of this series is. If you like, please let me know your reviews, and you also let me know that if any particular topic you want me to cover, which you are having difficulty understanding. Okay, so with that, thank you and bye bye.